All right, so here we go. 4, 7, 10, 13. We are looking for the nth term in the following sequence. N meaning if we want to relate where the number falls in the list to the number itself, or the value of that number, that's what we're trying to do. Set up a rule that works for all numbers in this list. So the first number in the list is 4. The second number in the list is 7. The third in the list is 10. And the fourth is 13. So, again, we're trying to relate a sub n to n in some way. I'm going to leave a space there. So, if I look over here, to get from one term to the next on the right, I'm adding 3. So we have an arithmetic sequence here, and you know it's arithmetic because of the fact that you are adding or subtracting. You have a common difference between the terms. Okay, so we take that 3 and we multiply it directly by n. And then we want to test out some of our terms, okay? So, if I were to plug in n into this expression, I should end up with what's on the right-hand side. Meaning if I plug in 1 here, I should end up with 4. So if I plug in 1, 3 times 1 is 3, but we want 4. So how do we get from 3 to 4 by adding or subtracting something? We have to add 1. Okay, so now let's go through and make sure that that works for the rest of them. 3 times 2 is 6. Does 6 plus 1 give us 7? Yes, it does. 3 times 3 is 9, plus 1 is 10, and then so on and so forth. So that is our expression, okay? Again, that's another one that should be relatively easy if you have prepared yourself. But that's like everything on this test, okay? You have to prepare yourself if you're going to do well. There's no way that I could do well in my job or any area in life, actually, if I was not prepared. Okay, what is the sum of this infinite geometric series? Whoops, that should be a 1, not a 2. Okay, so if we want to go through and actually add these numbers up. Okay, so 8 minus 4, we can actually continue this on if we wanted to. We notice that we're dividing by a -2 or multiplying by 1/2. So if we wanted to continue this on, we could add a half, minus 1/4, and so on. Okay, but either way, let's go through and do this. So 8 minus 4, that's 4. 4 plus 2 is 6. 6 minus 1 is 5. 5 plus 1/2, that's 5 1/2, and we could keep going on and on and on. But let's start at 5 1/2. All right, so if I look here, 5 1/2 or approximately 5.5, let's look at the fact that our answers, this is like one of the only times I'll have you guys use the answers to help guide you, because this is a problem that logic is very important in life, and this is a problem where using good logic is going to be very helpful. Okay, so let's look at this. 17 fifths, that's the same thing as 3 and 2 fifths. Okay, then 16 thirds, that's the same thing as 5 and 1/3. And then 2 thirds, that's like 0.67 approximately. So of all of these answers, which one is closest to where we ended up? Well, that would have to be that. Now, we also have a formula. I know for some of you really love formulas. A sub 1 over 1 minus r. That's the formula if you wanted to go about it doing that way, where this is a sub 1 and r, or the common ratio, is what you have to multiply by. And if you use that, you would end up with this expression. Okay? I think formulas are appropriate in some scenarios, but not always. Okay, so you really want to watch that. Logic outweighs formulas, in my opinion. Okay, so here we go. Gabby is setting up for her first gallery show as a professional painter. She has a blank wall to fill with 5 paintings. So let's put that, 5 spaces for paintings here. And she has 8 paintings to choose from. How many different arrangements are possible? Okay, so this is her first spot on the wall. If we imagine this is a big wall and she's going to put some paintings in here. So let's do that. 1, 2, 3, 4, 5. How many different paintings could go in this first space? Well, if she's choosing from 8, 8 could go in that first space. Now let's suppose that she's chosen one of them. So how many does she have left to put in the next space? 7. And then we go on and on and on. Well, she's chosen another one for these 2 spots, so now she has 6, 5, and 4. And then all we want to do is go through and multiply all of this together. Okay? So easiest way of doing this, because I know some of you are not a fan of dealing with large numbers like this, break it down into piece by piece. 6 times 5 is 30. 30 times 4 is 120. And then 8 times 7 is 56, so we end up with 56 times 120, which, yes, because you are not allowed to use calculators, you do have to do the long multiplication way. So anyone who needs review on that, please come see me. But if you multiply everything outright, you should get 6,720. Okay? All right, so let's do number 39 really quick. All right, 12 candidates in a city election, and candidates, okay, in a city election. The winner is the mayor, and we have the vice mayor. There. Okay. How many different combinations of mayor and vice mayor are possible without repetitions? Okay. This is a problem where I actually am going to bring back another one of those formulas, okay? We start with 12 candidates, and we're choosing 2 of them. C stands for combination, and combination is the one where there are not repetitions allowed. Okay, so this is 12 factorial over 2 factorial, 12 minus 2 factorial. Okay? There's also a logical way to look at it over here, but I'm going to stick to the formula on this one just really briefly, okay? So on the bottom, 12 minus 2 is 10. We can go down to 12, 11, 10 factorial. 2 factorial is 2 times 1, and then we have that 10 factorial over here. So those cancel each other out. 12 times 11 is 132, and 132 divided by 2, that is 66. Okay, so you could do the same kind of a process here. So 12 possible people for mayor, and 11 possible people for vice mayor, but you have to, because the problem specifies that you can't have any repetitions, that means you would have to divide out the fact that the mayor and vice mayor couldn't switch places. So you'd have to divide it by 2. So you end up getting the same thing, but you're looking at it in a little bit of a different way. All right, so either of those options works. All right, so we have a couple more. We have some probability and then some conic sections, and then we are done.